Ah, excellent. Hello. Am I audible? Is life great? Is the void still here? Let me just... Hey. Do 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 do. There's the COVID catching up to all of us. Nice, nice. This seems like a great number to start on. 3 people? Yeah, this seems like a good number. All right. Hello, all of you. This is the 2221/2121 seminar, part 2. You've all gone to part A, of course. If you haven't, slides will go up on the website, and there's the recording, of course, from last time. I will be presenting first today, and Gordon will come in later to do his thing. I'll be going over the initial boundary value problems and the first bit of Fourier series, and then Gordon will just go over the rest. Cool beans. So, starting off with the first bit, going over just a quick definition of what the inner product and what the norms are. So the inner product of two functions f and g, with this little notation over here, would just be the product of f and g and then integrated over whatever they were defined on. And if this inner product so happens to be 0, then f and g are orthogonal. Norm of a function defined using the inner product. The norm of a function is just the square root of the inner product of f with itself. So of course fx times fx just gives you fx all squared. So these are just two things you need to know before you jump into using all those formulas. So a quick example of just the inner product and the norm. We have two functions, sine x and cosine x, defined on 0 to pi. Finding the inner product and the norm. So we take sine x multiplied by cosine x, and they're defined on 0 to pi, so we're just integrating over 0 to pi. Use the double angle formula here. So sine 2x is actually 2 sine x cosine x, hence the half hanging around the front. And sine 2x integrates to negative cosine 2x over 2. Hence the half becoming a quarter, and then just sub in pi and 0. Which just evaluates to 0, since cosine 2 pi and cosine 0 are both 1. Norm of f would just be taking sine x multiplying by sine x again. Double angle formula again, but this time with the cosine 2x. But same deal, half integrates to x, cosine 2x integrates to sine 2x over 2. And then sub in the pi and 0. Sine just goes to 0 for all the bounds, and you're left with just pi over 2. So that's just a quick, demonstration of what the norm and the inner product are. If you got any questions, just chuck them in the chat. I've got an eye on the chat. Now, going further into the deeper end of life, knowing these excellent definitions, now you will see the secrets of the Cauchy-Schwarz inequality. So, absolute value of the inner product is less than or equal to the norm of f times the norm of g. You go ahead, memorize that, laser that into your skull, and add onto it the triangle inequality. So the norm of f plus g is less than or equal to norm of f plus norm of g. Hopefully you've seen the triangle inequality quite a bit before, with the whole, complex number topic behind you. But yeah, this is just another version of it with norms. So yeah, two inequalities, let that sink into your brain, and we jump into the meaty part, the boundary value problems. So we start off with the the definition, LU is equal to F for A less than or equal to X less than B, with B1U equals alpha 1 and BTU equals alpha 2. So the L here, there's the second order linear differential operator. It's operating on U right now. Pretty much this is what it will look like, but remember it's second order because the highest derivative is of order 2. It's linear because you can see none of the derivatives, the u dash dash, u dash, the u, none of these are raised to a power above 1. And the a2, a1, and a0, those coefficients would just be functions of x. And of course, differential operator, there's derivatives in here. So L is operating on the U right now. And the B1U and the B2U, B1 and B2, they're both boundary operators. And they operate on the U here. You can see B11 U dash A plus B10 U of A. So the first one is at the lower bound A, second one's at the upper bound B. You have your B11 and B10. Again, these are just some coefficients out there that are functions of x. These boundary operators, they're not going to go higher in derivatives. They're stuck at that U dash, that first derivative, thanks to your second order linear differential operator. This is just the general form of what it will look like. So, you have your boundary operators, your second order linear differential operators. You come across one of our first valuable theorems. If you have a homogeneous problem, so if your LU equals F, if your F happens to be 0, your boundary operators, the alpha 1 and alpha 2, both go off to being 0. That will be a homogeneous problem, and if it only has the trivial solution is of course just U being 0. If it only has the trivial solution, then for your inhomogeneous problem, which is just here, just a general inhomogeneous problem, it will have a unique solution for every F, alpha 1 and alpha 2, no matter what they are. That's a pretty powerful theorem. Definitely remember that one. And here's a beautiful demonstration of how important that theorem is. So we go to the 2018 final of 2221. We have the following boundary value problem. So we have LU is equal to P of D times U is equal to F of X. And U of A is equal to alpha 1, U of B is equal to alpha 2, A is less than B. So you have your P of D. They tell you P is a second order polynomial. So you're already getting the vibe, of course, that L is the second order linear differential operator. And your U of A and U of B equaling alpha 1 and alpha 2, those are your boundary operators. For the following cases, for what circumstances does a unique solution to the boundary value problem exist if P of lambda has two distinct real roots, P of lambda has a repeated real root, P of lambda has roots with non-zero imaginary parts. Alright, so going back up to here, you'll see that if you can prove the homogeneous problem only has a trivial solution, then you'll know that this inhomogeneous problem has a unique solution, and that's what you're going for here, a unique solution to the boundary value problem. So firstly, we're just going to convert this question into a homogeneous problem. So instead of f of x, now your f of x becomes a 0. Instead of the mysterious alpha 1 and alpha 2, now they're both 0. So with this setup over here, you have a homogeneous problem. And you just need to try and prove this homogeneous problem only has the trivial solution u equals 0. If you can't prove that, or if you just prove it's got other non-trivial solutions out there, then it means there won't be a unique solution to the boundary value problem. So starting off with part A, P of lambda having two distinct real roots. If you know it's got two distinct real roots, then let those two distinct real roots just be lambda 1 and lambda 2. And then you know the solution to the homogeneous problem is u equals a e to the power of lambda 1x plus b e to the power of lambda 2x. A and b are some constants out there. That is, of course, dependent on two distinct real roots, and you go through the other forms of the solution in the other cases. Now you know from the boundary operators here that u of a is equal to alpha 1 and u of b is equal to alpha 2. But alpha 1 and alpha 2 are both 0 now, thanks to the homogeneous problem. So u of a equals 0, u of b equals 0. You end up with these once you sub in the x equals a and x equals b. If your capital A happens to be 0, so for example here, this left-hand side going to 0, that will force your right-hand side to go to 0. And of course, exponentials being positive, it's not the exponential that's 0, it's your capital B that's 0. And vice versa, you have the same logic. If you know capital B is 0, then capital A has to be 0. That is, of course, the trivial solution, u being equal to just 0 plus 0, and it's 0. Considering capital A and B both not equaling 0, then what you can do is you can take left-hand side, divide by this right-hand side, negative b over here, you'll get a over negative b. And then the exponentials, once you divide them over, you have e to the power of lambda 2 minus lambda 1a. Repeat to the second equation, you'll get another negative a on b, but this time it'll be equal to e to the power of lambda 2 minus lambda 1b. These exponentials are equal to each other, so go ahead and equal the indices, and little a equals little b, which is a contradiction to the original question, since little a has to be smaller than little b, and you've just proved that capital A and capital B can't both be 0. So that means they both have to be equal to 0 here. Since you already proved if one of them 0, it forces the other one to 0. And that means overall U has to equal the trivial solution. And if there's only the trivial solution to the homogeneous problem, then the solution to your BVP is unique. And that's part A. The rest of the question pretty much follows the exact same tactic, provided, of course, you'll get different solutions just because of the different setups of the questions. So in part B, when you know it's got a repeated real root, instead of part A's form for the solution, you'll have this form, where lambda is the repeated real root. So U equals A e to the power of lambda x plus bx e to the power of lambda x. You still do the exact same method. So U of A equals 0, U of B equals 0, U sub in x is A, U sub in x is B. Both of these equal 0. So go ahead, equal those left-hand sides. And what do you know? If you factorize out the exponentials from both sides, it should be more clear that you can see the little a has to equal to little b, or your capital A equals the capital B. Because you're trying to equate off, your capital A equals capital B equals 0. Because you're trying to equate off those two sides, and if little a doesn't equal little b, you don't really have any other choice. You just have to force both sides to 0, and your exponentials aren't going to go to 0. So you're forcing that factor into 0. So you have these two choices over here. The second one, of course, gives you the trivial solution. The first one is a contradiction to the original setup, again, of the little a is less than little b. So you're only left with the trivial solution, and that means that the solution to your BVP must be unique. And part B follows that same way as part A went. And then part C. P of lambda has roots with non-zero imaginary parts. So your non-zero imaginary part root, that would be alpha plus I beta. So the general form U equals e to the power of alpha x times A cosine beta x plus B sine beta x. All of these forms are generally you should know them. Go back to that part 1 revision cinema if you're looking at this first line of the working and thinking, I've never seen this in my life. Gotta revise that one. But yeah, so this is mainly just testing you recognizing proving the trivial solution to the homogeneous means unique solution to the non-homogeneous. So subbing in x is A and x is B again for your boundary operators. Since you know both of the exponentials are positive, it must be the second factor over here that's equal to 0. So go ahead and equal both of those factors. And of course, just equating off those cosines and sines, you should be able to see beta A is equal to beta B plus 2 pi. So the two angles here, they don't necessarily have to be equal to each other. They can be apart by multiples of 2 pi, such as the cosine and sine. Both of those are 2 pi periodic functions. And that's it. If you can satisfy that restriction, then it satisfies both of those boundary operators, which means you have actually proved there are non-trivial solutions. You haven't been able to prove that capital A and capital B are both forced to 0. So your solution to the BVP is not unique because you can't prove there's only trivial solutions to your homogeneous equation. And yeah, that's a nice little demonstration of that theorem. Yes, I will be moving on. Just keep chucking in questions if you got any. Okay, now we get into even more of the fun stuff. This is where the true fun begins. You have, again, just the same setup as before, the linear second order differential operator. You'll never get sick of saying the whole name. We have this typical setup over here. We define the formal adjoint L star V as this. Second derivative of A2V minus the first derivative of A1V plus A0V. We also define the bilinear concomitant P of UV, which is equal to this. Just look at these two, memorize them, or, such as the joys of lockdown of open book, have them open somewhere. These are just the definitions of the formal adjoint and bilinear concomitant, and you just got to memorize them. Following from these two definitions of the formal adjoint and the bilinear concomitant, you get the Lagrange identity, which is the inner product of LU and V is equal to the inner product of U and L star V, so L star coming from the formal adjoint, plus P of UV, upper bound B, lower bound A. So you would sub those upper and lower bounds in the same way you would usually do in integration, just upper bound minus lower bound. And P of UV is, of course, the bilinear concomitant. So another identity for you to just memorize there. and a quick run through, you know, of just finding the formal adjoint, because yeah, it does look kind of interesting. All right, so we have the second order linear differential operator. Find the formal adjoint. So formal adjoint L star V is equal to, oh yeah, notice L star is just the operator here operating on the V. That V could be U or A or some other random variable. You just need to keep applying the exact same thing. So if this was L star U, that would just be A2U dash dash minus A1 U dash. It's just operating on V right now. So your L star V is equal to, so this is a direct copy of the formal adjoint definition from above. So the A2 in this particular question, the A2 would be here. It will be the x, it's the coefficient of u dash dash. Your A1 will be negative e to the power of x. And in this case, for minus A1 v dash, we just brought the negative out from the A1 to make it a positive in front. It's not really necessary, but it looks nice if you do that. It might be a bit less confusing when you enter the product rule. And your A0 is of course just x squared plus 1. So you just go in, sub in the A0, A1, and A2. Then you go ahead and apply product rule several times. So xv, apply product rule once, you'll get xv dash plus v, since the derivative of x is just 1. And e to the power of xv, again, you'll use the product rule. And e to the power of x just differentiates to e to the power of x. So you can see they're the same there. You have to use the product rule again on here, since it's the second derivative and you've only applied it once. So product rule again on the xv dash. You'll get xv dash dash plus v dash, which just combines with this v dash over here to give you the 2v dash. And then keep copying down the rest of it. And then do a little gathering. Gather those v dashes together and gather those v's together. And you have the formal adjoint. Looks pretty fancy. Do gather it finally into those v dash dash, v dash, and v terms. Don't leave them out separately. Yes. So what you can do, you know, there's not much use to it if you just have a definition and you're just finding it. What you can do with this, before that, another definition, formally self-adjoint. So an operator L is formally self-adjoint if L is equal to L star. So if the operator is just equal to its own formal adjoint definition. So a second order linear differential operator L is a formally self-adjoint if and only if you can rewrite it in this form. Because it is a pain to just keep finding the self-adjoint every time you need to prove formally self-adjoint. Instead, observe, if you can make L into this form, the negative pu dash dash plus q, and p and q have some functions out there. If you can make this form appear, then you'll know you've got the formally self-adjoint. And of course, you have the if and only if relationship, so it works both ways. If you know it's formally self-adjoint, you know it can be put in this form. If you know it's in this form, bam, you know it's formally self-adjoint. So we do have a set method for proving this. You don't just look at it and then, you know, wish out the correct answer. What you need to do is use the integrating factor method. The integrating factor here will be e to the power of a1 over, e to the power of integral of a1 over a2 with respect to x. So how this is going to work, you have your second order linear differential operator, and you want to rewrite it in the formally self-adjoint form. So using this excellent method of the integrating factor, a1 and a2 both happen to be x here. You can see the coefficients of u dash dash and u dash. And x over x is just 1, which integrates to x. So you have e to the power of x for your integrating factor. If you've forgotten how the integrating factor works, just remember you need to divide off that coefficient at the front there until it becomes 1. So divide x to every single term, and then multiply the integrating factor to left-hand side and right-hand side. If you've done this maneuver correctly, what you should end up with is the two terms at the front should be able to be collapsed down into this term using the product rule. So e to the power of x u dash differentiated should become these two terms again via the product rule. If you've done the above steps correctly. If they haven't worked out, then you may have not done the integrating factor correctly. Once you have this beautiful collapsed down form, you should be able to get into the formally self-adjoint form. You can kind of stop here and get to the formally self-adjoint, but you can also just multiply negative to everything just to properly check out the negative of pu dash dash plus qu equals g. Just exactly the definition of the formally self-adjoint form. And then you can just do a little matcheroo. So the p here is just e to the power of x. Your q here is 2e to the power of x over x. And your g here is this huge term on the right-hand side. And there's your formally self-adjoint form. If you're being particularly genre savvy, you'll probably see that the p is your integrating factor. And that can help you in some questions where you need p without the rest of it. Yeah, that's just a subtle thing. You don't really have to memorize that bit there, though. It doesn't take that long to get the whole form out. Yes, so that's getting to the formally self-adjoint form. Once you're in the formally self-adjoint form, you'll know the operator is formally self-adjoint. All right, so what you can do with the formally self-adjoint operator, if you've managed to prove it's formally self-adjoint, that means it satisfies this this very complex looking identity over here. The inner product of LU and V minus the inner product of U and LV is equal to sum from I equals 1 to 2 of this. I only equals 1 and 2. So all these things here pretty much just, it's all the cases. So we have B1U, B2U, R1U, and R2U. Now B1U and B2U are the exact same as before. They're the boundary operators. The R1U and the R2U are the more interesting things over here. So taking R1U now, you see U of A would just come from a boundary operator. Your B1, so not boundary operator, sorry, R1 is operating on the U, and then you can just U of A, whatever your A happens to be. Your B11 comes from your boundary operator over here. You see is the coefficient of the U dash A, and the P of A, that P comes from your formally self-adjoint operator. So you can see there are some advantages to just flicking out the integrating factor without having to go all the way down into the formally self-adjoint operator. You'll be able to get the P of A's here faster. You'll notice R1U has two different forms. They're both correct, and which one you use is actually usually just dependent on what the boundary operator happens to be. Like if your boundary operator happens to make B11 equal to 0, you can't use the first form, otherwise you'll be dividing by 0. And then you just use the second form because B10 will be non-zero. It really is up to that boundary operator there. And well, you'll see the example where you just choose whichever form you need based on which denominator isn't going to be 0. And R2U has a pretty similar definition, but of course it's at the other bound, the upper bound of x equals b instead of x equals a. So those are all the things that slap into the right-hand side over there. But we go even further. What we can do with the R1 and the R2U is this theorem over here, the Fredholm alternative. So these things over here, again, the usual setup. You have your second order linear differential operator, LU on the equaling to F. You have your boundary operators at x equals a and x equals b. This first part of the theorem, you already know. The fact that if the homogeneous system has a trivial solution, only the trivial solution, then your inhomogeneous system has to have a unique solution. What this theorem does is, of course, the other case, if your homogeneous system doesn't have only the trivial solution. So like we found before in part C, when you could actually find solutions that weren't trivial, if that's the case, then you can prove that your inhomogeneous system has a solution if and only if it satisfies this condition. The inner product of f and v is equal to alpha 1 R1v plus alpha 2 R2v for every solution v to the homogeneous system. So of course, the v, every solution to a homogeneous system, you would have found this if you've managed to prove that it doesn't have only the trivial solution. Presumably you found this mysterious non-trivial solution. So that's the v you will be subbing in. The R1 and the R2 are of course defined up here. These are their operators. Well, they're operating on the u here. You can see R1u, R2u. But they would do the exact same maneuver for here, R1v and R2v, but they're operating on the v. So for example, instead of u of a, it will be v of a. And you found v, of course, already, being the non-trivial solution. Alpha 1 and alpha 2, again, just should be given to you, being they're part of the boundary operators. F also given to you, LU is equal to F, and v, you found that. So all of those things should be findable by this stage. You know enough of the theorems. But, okay, saying that in practice is, of course, really nice, but So let's actually check it out. So this example, under what conditions does LU equal U dash dash plus U equal F, where U of 0 equals alpha 1 and U of pi equal alpha 2 have a solution? So of course you can try out, you basically hope it's the trivial solution case, like you get the homogeneous, you prove it's only the trivial solution, therefore you got a unique solution to your inhomogeneous. But of course, as you see here, the homogeneous solution, the U dash dash plus U equals 0, that is actually the equation U dash dash equal negative U, which hopefully you've seen enough of in those harmonics topics. The whole acceleration being proportional to negative of displacement. Its solution is just a sine x. But of course, this is not a trivial solution. The sine function isn't just zeroed out. So you found here v equals a sine x as a non-trivial solution to the homogeneous system, which means you're now in that second bit of Fredholm's alternative, where if you can prove it satisfies this fancy-looking condition over here, then you'll know the inhomogeneous solution system has a solution, which is what you need here. Under what conditions does it have a solution? So, transforming into formally self-adjoint form, so that way you can get the mysterious p function. You can try and get out the integrating factor, but in this case, you can actually just by inspection out the formally self-adjoint form. Remember, the formally self-adjoint form is negative of pu dash dash plus qu. The qu is just u. The q happens to be 1, and your u dash dash is just negative u dash dash, and then you slap a negative in front, and it returns to being u dash dash. So this is actually already in formally self-adjoint form, where your p is already this negative 1 over here. And that is a lot faster than trying to get through all the usual steps it takes to get to formally self-adjoint form. So don't do more working out than you need to. So you can see from here, since p of x is negative 1, that's all you really needed before you could start subbing in to the R1v and R2v definitions. So popping back up, you'll see R1u is defined by this. Remember, you have the two forms. You just choose it basically just based on your boundary operators. So B11 and B10, remember, they're the coefficients in your boundary operator at that lower bound there. So at the u of 0. So u of 0 is equal to alpha 1. That's your current boundary operator at that lower bound. And you'll see that u of 0 is the u of a in this scenario, and its coefficient is just 1. So there's your B10. Your B11 would have been the coefficient, if there was any, of your u dash. But you can see pretty clearly for both boundary operators, the u dash just isn't there. Like, there's no u dash of 0 plus u of 0 equals alpha 1. It's just u of 0. So your B11 and your B21 for that matter, they're both 0. So if you flip back up to your R1u and R2u, these two fractions, this first fraction over here and this first fraction over here, both of them you can't use in this question just because both their denominators head to being 0. So you just use the second form. So for R1 of u, that'll be negative p of a u dash a over B10. In this case, of course, your R1 is operating on v, so it'll be negative p of a v dash a over B10. But you won't be using the first form because its denominator is 0. So your B10 is 1, you'll see is the coefficient of u of 0. Remember a here, that's the lower bound, so it's happening at 0. So you sub in p of 0, a cosine 0, where the cosine just comes from the fact that v is a sine x, so v dash must be a cosine x. P of 0, remember p of x is always negative 1, just regardless of what x is. So that means p of 0 is negative 1, cosine 0 is 1, and this evaluates to just being capital A. You repeat the same process to R2v, except this time it's at that upper bound where b is equal to pi. But same maneuvers, there's no negative here, and your B20 so happens to also be 1. You can see the coefficient of u of pi is just 1. So go ahead, sub all of that in, and it's equal to capital A again. So you found the R1v, the R2v necessary for this second part of Fredholm's alternative. You know what alpha 1 and alpha 2 are. Well, you don't know what they are, but the questions called them alpha 1 and alpha 2, so that's it. You treat them as alpha 1 and alpha 2 if the questions called them that. So all you need is the left-hand side, the inner product of f and v. Once again, this question just gave you f, like that's it. They didn't tell you what f actually was. So when you're finding the inner product of f and v, it really is just leaving it as f of x. You don't have any other option here. you do know what your v is, of course. Your v is a sine x. So just by definition of the inner product, which you've hopefully remembered, you multiply the f and the v, so f of x and a sine x, and you just take those bounds over 0 to pi. And you can see here the bounds are defined from 0 to pi. So that's how you know which bounds to take for your integral. And you know it's equal to this right-hand side, where you've proved R1v and R2v are in fact both just capital A. Capital A can't cancel from both sides, and you'll be left, you'll be left with this beautiful condition, which you stare at for a bit and then realize that the question only needed a condition. So this is the condition under which, if you satisfy this condition, then your system over here, your second order system will have a solution, according to Fredholm's alternative. So that's what Fredholm's alternative is, ultimately. A lot of substitution, quite a lot of remembering the formula, but it is open book, so hopefully you have that formula hanging around. Any questions about this boundary section before we move on to the fabulous Fourier series? These are really excellent numbers. We're doing well. Nice. So, I have the generalized Fourier series. Okay, so this is the trig Fourier series. So we have the some function out there going from R to R, bounded, piecewise continuous, most importantly 2L periodic. So repeats every 2L, L is some constant out there, L could be pi. Like sine is 2 pi periodic. So L would be pi in that scenario. L is some constant depending on what the function is. The nth real Fourier polynomial of f is defined by this. So SNF is just that notation there for that Fourier polynomial. You have a0f over 2 plus sigma k goes from 1 to n. This huge thing over here, akf multiplied by cosine k pi x on L plus bkf multiplied by sine k pi x on L. You'll see this 2 is in red because it's really important to remember that divided by 2. It is such an easy thing to forget. Like you find a0f, you find akf, you find bkf, and then you just sub it in. So you gotta remember a0f divided by 2 is that actual first term. It's not just a0f. So be wary of that one. So a0f is defined by 1 over L multiplied by integral from negative L to L of f of x. AKF is defined by 1 over L integral from negative L to L of f of x times cosine k pi x on L. And once you find AKF, you do still sub it back into here and multiply it by cosine k pi x over L. That's just how the definition goes. In BKF, pretty similar, but the cosine is a sine. So you do find the A0F separately from finding the AKF. So k would just be greater than or equal to 1 here, since it won't be equaling that 0. That's its own little special case. Now, this does look rather complicated. Like, it looks like a lot of working out to remember. What you can do to simplify this, which usually happens quite a lot in these types of questions, is that f is usually an even or an odd function. And then that lets you do a little simplification just by some nice integral properties. So, for example, your a0f, remembering that your a0f was defined by this over here, if your f of x happens to be even, it will just be double of 0 to L instead of just 1 of the negative L to L. And that can speed up some of your working. Same thing for the AKF. Since f of x is even and cosine is just also even times even returns you to another even. So you use that same property again. More importantly, BKF goes to 0. So that's just because f of x is even, sine is odd, even times odd, returns you to that odd function. So your PKF, which goes from negative L to L, it in fact goes off to 0, and you don't even have to worry about finding it. So just recognizing that f is an even function pretty much removes like half your working. You just have to find AKF and A0F. Same thing for if f is odd. It's the same reasoning. A0f and AKF both become 0 just because an odd function times an even function gives you back that odd function. Your BKF stays hanging around and just doubles a bit and goes from 0 to L because odd times the odd function gives you back that even function. So that's the f of x times the sign. It just goes back to being the even function. So if f is an odd function, you can save half your working out time just by not finding A0f and AK. Well, not finding, but recognizing they're both 0. So you don't have to put in the hard work of trying to integrate, which gets really hard sometimes, just really tedious. So make sure you recognize if f is even or odd, there's some simplifications to be carried out. And let's try out a nice question. So find the real Fourier series of f, where f of x is equal to x for -1 less than x less than equal to 1, and requiring that f of x plus 2 is equal to f of x. So your f here in this scenario, you see it's 2 periodic, which means it repeats every 2, and that's just being picked up from the condition that f of x plus 2 is equal to f of x. So as x increases by 2, it just goes back to the same function value. And this is an odd function. F of x equals x. It's your typical straight line gradient 1 intercept 0. So this is a 2 periodic odd function. Because f is odd, you recognize from up here that A0f and AKF are both 0. So you don't need to work them out. All you need to do is apply this fabulous formula for BKF, and you have all the coefficients you need for your Fourier series. So BKF is equal to double of 0 to L. Now normally it's 2 over L in front, but the L in this case is 1. Remember, L is defined by your function period. So your function is 2L periodic. Because it's 2 periodic here, that just means that L is 1. So 2 over L is just 2 over 1, hence it's just 2 at the front here, and 0 to L becomes 0 to 1. Your f of x in this question is just x, and L, once again, it's 1, so just sub it in, and you have sine k pi x. So you have this lovely integral over here, which you can use the power of integration by parts on, where you'll just be differentiating that x and integrating that sine. So go ahead, plop that stuff down. What you end up with is this expression over here, where the sine k pi is in fact just 0, since sine of multiples of pi is 0. And cosine k pi is just -1 to the power of k. You can go ahead and memorize that one. It doesn't take that long to think of it by yourself. The cosine of multiples of pi just go between 1 and -1. The -1 to the power of k, of course, ensures that you have the right sign. So cosine 0 gives you 1, cosine pi gives you -1, cosine 2 pi gives you +1, cosine 3 pi gives you -1, etc., etc. Go ahead, sub all of that stuff in, and you end up with this expression. The sine k pi goes off to being 0. You have cosine k pi being -1 to the power of k, which you multiply by the -1 in front here to give you -1 to the power of k plus 1, which is where this term comes from. Your k pi over k squared pi squared is what reveals the k pi in the denominator, and the 2 here in front in the fraction carries on to over here. What you'll be left with, of course, so the 2 times -1 to the power of k plus 1 over pi k. And then that's the coefficient, the bk, and if you flip back up to over here, bkf is multiplied by sine k pi x on L, and the sigma goes from k equals 1 to n. AKF and A0f are both 0, so don't worry about those terms. Just take your BKF, multiply it by sine k pi x on L, where the L is 1, so it's just sine k pi x, and you have your sigma going from 1 to infinite. And there it is. There's your real Fourier series, just by applying that definition and taking advantage of the nifty fact that your A0s and AKs just all go off to being 0. Otherwise, you'd have to do another integration by parts just to work out the x times cosine k pi x, which is a lot more work than necessary. And another interesting thing just about the Fourier series. So, your Fourier series, normally, of course, let's go through the theorem first. Suppose your function, whatever function they give you, has a jump discontinuity at a. So that means at this particular x equals a point, if you approach it from the right hand and the left hand side, so from a plus and a minus, your f actually goes to different values. So the limits exist, but they aren't the same as each other, which means your function just jumps around that x equals a. If this is the case, then your Fourier series at that particular x equals a point would approach the average of those two limit values. And what that means, so consider the f of x from before. Remember, it was periodic every 2. So you would have this base, y equals x, and then it would repeat again. So like over here, that's a repeat, 2 back. Now, just by the definition of how this Fourier, so -1 less than x less than equal to 1, you would have been open circling at a -1 and closing circling at 1. So this thing over here, you would have closed circle at -1 and open circle at 1. Then you see that discontinuity jump from -1 all the way to 1. But when it comes to the Fourier series, so this is not in fact the original y equals x2 periodic. This is us sketching the Fourier series. And the Fourier series is just, usually it's all the same of your original, but at that discontinuity, instead of taking one or the other value, the Fourier series takes the halfway value. So 1 plus -1 is equal to 0. And you can see same thing happens over here. Your periodic function, once it started repeating, would have started back down at -1 and gone up. But your Fourier just takes the halfway between that discontinuities and bam, it's just at the 0 there. So that is how you draw the Fourier. If your original function goes across a discontinuity, it's a nifty little fact. Remember that one, or you'll be drawing the Fourier series in an interesting manner. It will look very nice, very similar, except you'll be missing that crucial correct point where the jump discontinuity happens. But that's a little sidetrack. I suppose that this is more relevant. Your half-range expansion. So normally, like before, they define that function for you just over that full period, but sometimes they just define it over half of it. So instead of -L to L, they just define it over 0 to L. And what you can do in this scenario, this definition looks a bit funky. Let's go to this geometrical, illustration. So this thing in red here, say that's all they give you. Like they give you this mysterious function. They tell you, hey, it's 2L periodic, but we'll only give you this function over like just L, so not over 2L. What you can do with this, because the Fourier series is so nice to find when f is even or odd, you can just force it into an even or odd function just by extending it a bit. So this thing on the left, if you just reflect it across the y-axis a bit, suddenly you've got an even graph. And exact same curve in red, but this time do a little rotation such that it's got an odd symmetry. So if you rotate it 180 degrees about the origin, it just be back on itself. So these are both valid extensions of your original red curve, but one of them's even and one of them is odd. And describing it algebraically, your odd extension would just be -f of -x for that -L to 0, and your even extension would be f of -x for -L to 0. But that's the algebraic definition there. It really is just describing these pictures. So what you can do, so consider this f of x equals x. So it's the same, kind of the same function as before, but instead of being defined over the -1 to 1, it's only defined over 0 to 1. Now, we technically could extend this with an odd extension, and then you'll have exactly the same question as before, f of x equals x. But let's instead consider an even extension, just because. So, for your -1 to 0, you have y equals -x. So you have one of your absolute value functions, which is clearly even. And it includes the bit the question gives you, the f of x equals x, for 0 less than x less than equal to 1. So, because we've got an even expansion going on, this time your bk's go off to being 0. So you don't have to find those, but you do have to find your ak's and your a0's. So your ak will take 2 over L, your L is still 1, 0 to L, your L is still 1, and then your f multiplied by cosine k pi x on L. So your f is x, your cosine k pi x on L is just cosine k pi x. This is an integration by parts where you're differentiating the x and integrating the cosine k pi x. Doing your usual substitutions here, sine of multiples of pi just goes to 0. So this entire first term over here just disappears, and you just need to integrate sine k pi x again to become cosine k pi x over k pi. Sorry, negative cosine k pi x over k pi. So those two negatives become a positive. That's where that negative disappeared off to. And then you sub in the 1 and 0. Interesting things to note here, of course, cosine k pi minus cosine of 0 just being 1. So cosine k pi minus 1 When your cosine k pi is 1, the whole thing disappears and it's just 0. Or if your cosine k pi is -1, you have -1 minus 1 to give you -2. And a -2 times 2 is what gives you this -4. So that's just the two scenarios over here. When k is odd, cosine k pi will be -1, and when k is even, cosine k pi will just be 1. So that's why this equals 0 when k is even, and equals -4 over k squared pi squared when k is odd. A0g, remember you evaluate this separately from the AKG. So instead of x times cosine k pi x, you just have x. And evaluating this, going from 0 to 1, you'll get a nice little 1. And BKG is 0, as I said before, since this is an even extension. So working out your Fourier series, very careful. Your first coefficient over here is A0 over 2. Remember that for life. Don't just write down the 1 from the A0. It's 1 over 2. And then you have AKG multiplied by the cosine k pi x's. Except, of course, you already proved AKG goes to 0 every time k is even. So instead of the usual sigma, where k just goes from 1 to infinite, this time you just write k is odd. And that shows that these terms are only non-zero whenever the k is odd. So you'd be subbing in like k is 1, 3, 5 into this expression over here. And you don't even write the expression for when k is even, just because ak is 0. So it wouldn't be there. And that's your nice little Fourier series, just by carrying out an even extension. You could have done an odd extension, but then you can just refer back to the previous question. It will just be the same question again, because it will just be f of x equals x. Getting into orthogonality of functions, we already had an orthogonal definition from before when we said the inner product is equal to 0 and that makes f and g orthogonal. This is pretty much very similar definition, except we're just introducing the weight function. So the inner product of two functions with respect to the weight function. So this definition is very similar to the inner product. We just slap in the w of x inside that integral product there, and you have a little subscript w next to your inner product to show that you're taking the inner product with respect to a weight function. Now this weight function is bigger than 0 on the a to b, and the two functions still, they're defined as being orthogonal if your inner product ends up being 0. But this time it's the inner product with respect to the weight w. So w of x would just be inside your integral. We can extend this to sets of functions. So consider you have a set of functions, f1, f2, yada, yada, yada. This set will be orthogonal if you can take any pair. So you see here, n is not equal to m, just ensuring that we're actually taking a pair of functions and not just like the same two functions. If fn and fm's inner product with respect to the weight function w is 0 for all the pairs, then this set overall is just orthogonal with respect to w. It's a nice little definition there, and a demonstration of just how to prove it. We have a set of functions, so sine m pi x over a, where n is 1, 2, 3, 4, whatever, show that it's an orthogonal set on 0 to a with respect to the weight function 1. Because the weight function is 1, you barely notice it being there. Like, it barely changes anything. Like, you have the yn, ym, where n's not equal to m, just showing you taking the pairs. You have the little 1 subscript to show the weight function is 1. But when it comes to the actual working and you have to show 1 inside your integral, you don't even show it. Like, 1 multiplies the signs, sure, but you don't really need to write 1 times. You can, just to show you understand where the weight function is. But yeah, just writing this is fine. So sine m pi x on a multiplied by sine m pi and x on a, and you're proving it's an orthogonal set over 0 to a. So you see your bounds go from 0 to a. To solve this integral, you use product to sum. If you don't remember it, just like, bippity bop in the Google, it really is just a formula. So your two signs there, this product just becomes cosine minus cosine, and those two angles are taken from the two angles of the sines. So the first one is first angle minus second angle, and this one over here is first angle plus second angle from your two sines there. Both of these cosines integrate to sine of a multiple of pi. So when you sub in your bounds, it's just 0. Sine of multiples of pi is 0. So you've proved that this inner product of any two pairs from this set is always 0. So overall, this set is orthogonal. And that's a nice little neat proof over here. Oh, right, yeah, the norm can also be defined with respect to the weight function W. Same thing as before. You can see since the norm is defined with the inner product, then norm with respect to weight function, you just use inner product with respect to weight function. And you can see the weight of x, again, gets slapped into your integral. And then just multiplied by the usual definition of how you find norms. So fx all squared there. So using the same set from before, just a little practice of finding the norm with respect to a weight function, except the weight function is 1. So once again, you just don't see it. It's like 1 times sine squared m pi x on a. Picture that weight function shoved in there, but then you don't even write it. So solving this one, pretty similar to a question from before, it's just double angle formula for cosine. So yoda yoda, go ahead and solve that one. It's the same deal as what we did in one of the previous questions when we found a norm. More importantly, all these, raw weight function definitions, they're all in service of the generalized Fourier series. So the Fourier series we found before, that was pretty specific. It had a bunch of sines and cosines, which we have in fact proved by this point. All the sines are orthogonal to each other. So that's in fact just one of the special cases of your generalized Fourier series. So it should work for any orthogonal set of functions. So before we had the sines and cosines as your orthogonal set of functions, but as long as you have some orthogonal set out there, you can make a generalized Fourier series out of them, which is defined by this. You have this sum going from n is 1 to infinite of Cn times phi n, where the Fourier coefficient here is the Cn. Your phi n is, of course, your orthogonal, is the functions from your orthogonal set. So in the before life, that would have been sines and cosines. Here, it's just whatever happens to be your orthogonal set. Your Cn is defined by the inner product of f of phi n with respect to w over the norm of phi n squared with respect to w. So orthogonal sets, your sines and cosines happen to just be orthogonal with respect to the weight function 1, so you didn't really notice anything. But if you have some other orthogonal set that's only orthogonal with respect to some other mysterious weight function, you will have to adjust for that when you find Cn. So Cn is the nth Fourier coefficient of f with respect to whatever set of orthogonal functions you have. Now, 2221 elite example, the completeness of an orthogonal set. So we already have the definition of the orthogonal set. I'm just adding on another definition. It's complete if there's no, so you have a set of functions. If there's no other function, like some mysterious function outside the set, and that function can't be orthogonal to every function in your apparently complete orthogonal set. So if you have a set of functions and you've already decided, yeah, it's a complete orthogonal set, you shouldn't be able to find some other non-trivial function out there that's also orthogonal to every function in your set. Otherwise, it should be in there because you should have a complete set. So that's just what this algebraic definition is over here. If for every phi belonging to this complete orthogonal set you apparently have, if you have some mysterious function f out there, which when inner producted with phi becomes 0, in other words, f is orthogonal to every function in your set, then that mysterious f should be 0. It should be trivial. It shouldn't even be there. If you prove it's not 0, then you don't have a complete orthogonal set anymore. So yeah, that's just a little algebraic definition there for the complete orthogonal set. Now, what you can do with the complete orthogonal set is make the Parsifal's identity. It's such a great identity. So if you have a complete orthogonal set, and then AK is just the kth Fourier coefficient of f, then you know the norm of f squared with respect to the weight function is equal to sigma k goes from 1 to infinite of ak squared multiplied by the norm of phi k squared with respect to the weight function. So your phi k's, of course, come from your complete orthogonal set. AK you find just from your beautiful Fourier coefficient definitions, whether it be that generalized Fourier definition or you're just using the typical sines and cosines. So you'll just find the AK is the usual way we've been finding them in examples so far. And the F, it's just whatever F happens to be in the question, of course. If you're in 2221, you can also take the converse of this theorem. So if you're just in the 2121 life, if it's complete orthogonal, you can use Parsifal's. But if you're in 2221, you know that if you can prove Parsifal's, then you can actually say it's complete. So it's another way of proving complete orthogonal sets without using that definition, this one over here. You can try and prove Parsifal's instead. So that's a pretty nifty thing there. And just a demonstration of the power of Parsifal. We have this given f of x equals x squared over negative pi to pi. hence show blah. Just when you see mysterious things like this that involve Fourier and you have to prove some identity out there, this just an identity that involves that sigma and going from 1 to infinite. It's just, yeah, you should 1 over n to the power 4. That's a mighty interesting high power you've got there. It comes from particles. So checking out how that works. So firstly, before you go through all that interesting stuff, actually finding the Fourier coefficients, generally we stick with the trig Fourier series. Like I know I just went through a whole, wow, it works for any complete orthogonal set, but also it just works for sine and cosine. You just use the usual suspects we've been using so far. So you use A0F and firstly, F is even, so we don't find BKFs. BKF is just 0. And then we find A0 and AK with the usual tactic style. So A0 is found by integrating the F, and AK is found by integrating F multiplied by cosine K pi x on L. But the L is pi. So that's where the K pi x, where that pi disappeared off to. L is pi just because here's defined over negative pi to pi. So 2 pi periodic, your L is pi. This is actually 2 integration by parts, where you keep differentiating the x and integrating the trig. That's all the in-between work in there. You just got to remember that the cosine kx will be equal to negative 1 to the power of k. That's where this negative 1 to the power of k keeps popping out from. So to apply the particles identity, so in particles, remember we needed the Fourier coefficients, which we've already found, it's ak squared. We need the functions for your mysterious complete orthogonal set, but we're just using the typical sine and cosine one, except for the fact that BKF is always 0. So that Fourier coefficient multiplied by its corresponding function from the orthogonal set, you're not going to have any of those BK ones there, so you don't even need to worry about the signs. You just need the cosine KXs, because they're the ones with the AK coefficients that will actually appear, because your AK is that 4 times negative 1 to the power of k over k squared. And this 1 over here, that's just the corresponding function to this A0. So finding the norm over this squared, because remember, particles is norm of phi k squared. And you have a little 1 down there because your sines and cosines are orthogonal with respect to the weight function 1. But as I've said before, when the weight function is 1, you hardly really notice anything. So you have the 1 squared, the cosine squared kx, integrate both of them. Second one, you will be using a double angle formula. We did that a bit before, a few times, so you can look back for that double angle working for the cosine. You also have, remember, on the left-hand side of your particles, you have that function, whatever the function is, in this case, x squared. You have the norm of that squared with respect to w. So again, x squared becomes x to the power 4, and your w happens to be 1. So 1 times x to the power 4 is just x to the power 4. So reverse power rule that one, and then sub into the particles identity. So this goes on to the left-hand side of particles identity. You have the A0f, remember the 2 pi squared on 3, but the actual Fourier coefficient is A0f divided by 2. Never forget that. A0f divided by 2 will catch out quite a few people. So you have 2 pi squared on 3 and then divided by 2. All squared multiplied by the 2 pi. Remember the 2 pi comes from its corresponding functions, norm squared. You have the AKF, square that one, and then multiply it by its cosine kx norm squared. So that would be this pi over here. So that's where this pi comes from. And you have a sigma. K goes from 1 to infinite. Typical Fourier style. What you should be able to do, you slap the 4 squared outside of the 16, slap the pi out, evaluate this stuff using your calculator, and you should be able to see. You have that k goes from 1 to infinite sigma of 1 over k to the power 4, which is what you're aiming for with this question. Well, technically you're aiming for 1 over n to the power 4, but that's just a dummy variable away. You just have to do a correct little rearrangement there, which is just subtraction, dividing by 16 pi, and you get pi to the power 4 over 90. That's a really neat use of particle identity. This one comes from the 2015 paper. If you look carefully at this one, it is also the sum of 1 over n to the power 4, and you do prove pi to the power 4 over 90. So that's actually just all the same working. Just a nice little thing at the front there. Just part A and part B. So yeah, part C is pretty much the same working as above. A little difference there because f of x is 2x squared minus 1, but ultimately is the same working. Now we have sketching a graph of the Fourier series. So 2x squared minus 1 is the parabola shifted down by 1 unit, so here. and it's defined over -1 to 1, and it repeats every 2. You only sketch for -2 to 3. You also technically sketch in a Fourier, not the f of x. But there's no weird discontinuity, so you don't have to worry about weird taking the averages. You can see each period just joins up nicely, and you just stop here halfway through a period, because they tell you to only sketch over -2 to 3. And when it comes to finding Fourier, you'll just find a0 the same way, integrating the f, and you'll find an by integrating f multiplied by the cosine m pi x. This time, of course, the pi doesn't disappear because it's not periodic over the 2 pi, it's periodic over the 2. So your L was just 1, and you'll be left with cosine m pi x instead of just cosine nx. But it's the same working as before, pretty much. Do a little integration by parts. You end up with this. And then, of course, your bk's all go off to being 0 because your function was even originally. And you have your Fourier series. And part C is just Parsifal's identity. But the exact same working as before, pretty much. You just have a little adjustment there because it's 2x squared minus 1 all squared instead of just x squared all squared. But after a nice amount of cancelling, you end up with just the same answer as before. Sorry, I am just trying to speed through this just because I've seen we've hit that 4 o'clock mark, so it's time for me to, pass off the baton to Gordon. Yeah, so Gordon will keep going from here. I will go ahead and just end my stream so Gordon can jump on. Yes. Hasta la vista.
Hello there. I'll start at 4 or 5, so just to give a little break. Okay, time to start. So since it is 4:05, hello everyone. Hello Wendy. Thanks for presenting the first half. And now I'll finish off the rest of 2221. So continuing on, we have Sturm-Liouville equations. And that refers to any equation that is written in this form. So any equation that can be rewritten in this form is called a Sturm-Liouville equation. And basically that's all it is. So where this comes from is that if we rearrange this, so we move this and this over to the right hand side, we get lambda rx equals minus p of x u dash dash of plus q of x u, and this was our self-adjoint form. So essentially we just have a self-adjoint operator plus this lambda rx term, and that is a Sturm-Liouville equation. And the conditions for it are that p of x and rx have to be positive over this interval. And suppose we make this self-adjoint part LU, then the solution to this LU equals lambda RU the solutions are called Eigenfunctions, or the non-trivial solutions are called Eigenfunctions, and the respective lambdas are called Eigenvalues. So this is and there's also an R here, and this R forms the weight function. But often we set I equals 1, and then it just becomes lambda u. So this is similar to in linear algebra, where we have the concept of eigenvectors and eigenvalues. So when we have AV equals lambda v, so instead we have LU equals, or let's call it L phi equals lambda R phi. So the phi forms the eigen function, and the lambda forms the eigen. The corresponding lambda forms the eigenvalue, and this is what we call an eigenpair. So sometimes the question might ask for the eigenpairs, and that is what you're supposed to give. So we have this question, which is given this Legendre's equation, write this as a Sturm-Liouville equation. So once again, a Sturm-Liouville equation is any equation that can be written as p of x u dash dash plus lambda rx minus q of x equals 0. Hopefully you don't mind the color. I was just trying to use a variety of colors. Yes, my straight lines. This is as straight as I can draw them. Anyway, so I want to reform it into this form, and similar to the self-adjoint, we use the integrating factor. So we let px equals to exponential. We find the integrating factor first, which is the integral of a1, which is minus 2x, and divided by a2, I think, or was it a0? I think that's a2. Divided by 1 minus x squared dx, and this becomes exponential integral of, actually, it becomes log of 1 minus x squared, so we ignore the constant of integration, and this becomes 1 minus x squared, which is our first term, so that's nice. So we don't have to divide by anything. And then, so we try to differentiate. So we take this term. So this gives us our u double dash or u double prime using the product rule. And then when we differentiate this, we get minus 2x u dash, and this just happens to be our second term here, so then we just need to add the final term for it to be equal. So plus nu nu plus 1 plus nu, u, nu plus 1 u. And we've essentially written it in Stern-Liouville form. So just rewriting it onto one line, it becomes 1 minus x squared u dash plus nu plus 1 u equals 0. And then our p of x is just 1 minus x squared. Here we don't have a q of x, this is just lambda r. And we just set rx is equal to 1 to make our lives easier. And then lambda becomes nu plus 1. And qx. So there's no qx here, so qx is 0. So this is how our equation forms. And then over what domain is this equation Stern-Liouville? So let's say in the previous slide, if you ignore my scribbling, p of x and rx have to be positive. So here r is a constant, but px has to be positive. So 1 minus x squared has to be positive. That means x has to be in the interval minus 1, 1. Minus 1. I don't think this Stern-Liouville equation's that beautiful, but maybe that's because I don't really understand it. But okay, moving on. So, with that. So we define a regular Stern-Liouville eigenproblem as a problem where we have this rearranged. So essentially, we have the Stern-Liouville equation where the Stern-Liouville equation equals 0, and we move this lambda over. But we also have two boundary conditions, and these have to be non-trivial. So this line means they have to be non-trivial, and this line just means it's not singular. So the leading term, the p, doesn't disappear at the boundaries. So this is what we define as a regular Stern-Liouville eigenproblem. And when we have a regular Stern-Liouville eigenproblem, well, actually went out of order there. So all this is, actually I might just jump. Okay, yeah, so when you have a regular Stern-Liouville eigenproblem, then the eigenvalues that we get will be real. But more importantly, the solutions that we get, which are the Eigenfunctions, will form a complete orthogonal system over the interval AB with respect to the weight function. And additionally, these eigenvalues, when reordered, the eigenvalues will go off to infinity. And this you'll see from this example. So I've talked a lot about these theorems, but really the Stern-Liouville eigenproblems, they're just another type of differential equation. It's just a type of differential equation that can be written in a specific form. So here, this is a Stern-Liouville eigenproblem. It's fairly straight. Should be fairly straightforward. It's just a second order differential equation, except the difference being we have this lambda, which is unknown. So find the eigenpairs. Essentially, what it's saying is that if we move this over, so get minus u dash, basically solving minus u dash dash equals lambda u. And so the solutions will be eigenpairs, and we'll write LU. So finding the u's, so the eigenpairs are essentially finding the solutions and the corresponding eigenvalues. So we just solve it normally as we would with any differential equation. So in this case, what we do, since lambda is unknown, we consider the different cases of lambda. So these generally all go the same way. So first, we start with lambda equals 0. Then we have our equation becomes u double dash equals 0. And then if we integrate that twice, we get two constants. So it becomes u equals ax plus b in the most general form. And then we have two boundary conditions. And these are important to finding the Eigen functions. So we sub it in, so sub in u equals 0, so that means b equals 0, since a times 0 is 0. Then that means our solution is u equals a. However, if we sub in, what implies it? U equals 1 equals 0, that implies a times 1 equals 0. So this is a trivial solution, and as mentioned, so our eigenpairs, which says here, so our eigenfunctions have to be non-trivial, so we don't care about our trivial solutions. So we just discard this case. So our next case is when lambda is negative. And the way we do this, we set it to equal to negative k squared. Equals negative k squared, which will be negative assuming k is real, and we'll say k is real. And actually we'll find k, so not in this case, but so this is how we define k lambda to be negative. And the k squared is nice because this then becomes u double dash minus k squared u equals 0. And then because we have the k squared, then our general solution becomes e to the kx plus b e to the minus kx. Since if you get the characteristic equation, we get k and minus k. I think in the slides it's written as cosh and shine, so you can always solve. So cosh and shine is an equivalent way of doing this. It's not the same. Your coefficient estimates. So here, in this case, cosh and shine were found. So the coefficients, so these will not be the same. These estimates for a and b will be different, but the solution will be the same once you sub in the values. So that's why we say it's equivalent. Just do whatever you're used to. For me, the e to kx form is easier, so I'll just do that. So once again, we sub in the boundary conditions. So u of 0 is equal to a, e to the 0 is just 1, so just a plus b. That's equal to 0, so then we can write b as minus a. And then if we sub in 1, that equals to a e to the k, and b is minus a, so minus e to the minus k, and that's equal to 0. So factoring that becomes e to k minus e to minus k equals 0. So either a equals 0 and b equals 0, and that means we have a trivial solution, or we have k equals 0, and then this becomes 0. But if k equals 0, then since lambda equals minus k squared, lambda equals 0, and that was our first case. So again, this forms a trivial solution. So our final case is when lambda is positive, so we set equal, once again, with k squared, and then we have u double dash plus k squared u equals 0. So solving this gives us a cos kx plus b sine kx. And once again, solving the initial condition, so u of 0, so cos of 0 is 1, and the sine of 0 is 0, that's equal to 0, so then we cross that out. And then u of 1 equals 0, so u of 1 equals b of sine k, and that is equal to 0. And we could let b equal 0, but that's a trivial solution. And here we actually have another solution, which is when k is equal to n pi for any integer, and this will give us a solution that is non-trivial. So our solutions, which we call our eigenfunctions, will just be this, so b and k was n pi, so n, so we don't need a b actually. Will be sine of n pi x, and then the corresponding eigenvalue, which was our lambda, if you remember. The lambda is the eigenvalue. Lambda n was k squared, and k is n pi, so that's n pi squared. And this is for n equals 1 to, and not for n equals 0, since we don't want the trivial solution. So these form our eigenpairs. This is our eigenfunction, and this is our eigenvalue. And as we can see, so as we can see, our lambda n here, as n goes to infinity, then this will go to infinity. So that holds up with what we said here. And now show that the eigenfunctions are orthogonal. So as Wendy mentioned, to show that they're orthogonal, you just take the inner product, which in this case is just the integral within the bounds. So here the bounds are 0 and 1. So we just have to show that. Actually, don't want to do this one. So we have to show that this integral with respect to the weight function, and in this case, our weight function was 1. Since if we go back, right? So this lambda u is basically lambda r u, so r is 1. So this is, even though this should be a weight function with respect to r, rx is 1, so it doesn't factor in here. And to show that this is orthogonal, basically we just need to show that for any two eigenfunctions, any two distinct eigenfunctions, the inner product is 0. So the inner product is the integral from 0 to 1 of their product. So we just get sine n pi x and sine m pi x, since we want a different m. And then we just do this integral, so with two sines, we just do the products to sums. And since it's sine, we have to get cosines. And once you do this, so since n is not equal to m, we can do this. We can take the n minus m out, and also n and m are positive, so n plus m won't be equal to 0. And then this integral, so once you sub in 1 and 0, will equal to 0. And generally when you do these integrals, you'll always, when you get sine or cosine, you always get 0, because when you use the products to sums, they'll become a sum or difference of cosine functions. And then once you integrate the cosine functions, you get sine functions. And when you sub in sine times any integer times pi, you get 0. So generally speaking, these will tend to equal 0 as long as n and m are not equal, and n plus m is not equal to 0. So with this, we showed that since the inner product is 0, the eigenfunctions are orthogonal. So here I have another example. So generally these Sternum-Liouville equations, they either consist of this problem where we have to show that it's Sternum-Liouville form, or we just solve them like regular second order differential equations. So part A, transform this into Sternum-Liouville form. So once again, we just find the integrating factor, which is exponential of integral of a1, so minus x divided by square root 1 minus x squared. Okay. Divided by a2, square root 1 minus x squared, and then dx. So then this becomes exponential of integral of minus x divided by 1 minus x squared dx, which is exponential of half times the log of 1 minus x squared, and we ignore the integration constant, and this just becomes square root of 1 minus x squared. And this is our first term here, which is nice. So then to transform it into Stern-Liouville form, we find this, that was square root of 1 minus x squared. So that's equal to square root of 1 minus x squared u double dash, plus we differentiate this bit, so that becomes minus x over square root of 1 minus x squared. So there's a 2 here and a 2 on the bottom, which cancel out, and then u dash. And this is our once again, this is our second term, which is nice. So we don't have to do any rearranging. We just have to add the final term. My nose, it wasn't as good. And then our equation is equal. So just rewriting it to make it nicer, we have square root 1 minus x squared u dash dash plus nu squared over square root, there's a u here, 1 minus x squared, I keep forgetting this u. So then p of x equals to square root 1 minus x squared. Q of x is equal to 0. So this is equal to lambda r. So we let lambda equals nu squared. They're basically v's, but it was a nu at one point. And rx is equal to 1 minus square root 1 minus x squared. So part B, if the eigenfunctions were to form an orthogonal set on the interval AB, what equality must two of these functions obey? So going back, we look at regular Stern-Liouville eigenproblems. We say that if the problem is a Stern-Liouville eigenproblem, then we get this property where the eigenfunctions will be orthogonal. So basically, we just need the solutions to be eigenfunctions from the regular eigenproblem. So in order for that to hold, essentially, so we have this bit, which is the equation, and basically we just need the two boundary conditions. So that slide. So basically we just need two non-trivial boundary conditions at the boundaries A and B. And if we have these two boundary conditions and the boundary conditions equaling 0, then this will mean that our solutions are from a regular Stern-Liouville eigenproblem, and the solutions will therefore be orthogonal. So in the case of a singular Stern-Liouville eigenproblem, we just look at this one, which is this one was the Bessel equation back from chapter 1. And essentially this is saying that if we have this specific form, so just a Bessel equation but with this lambda here, and we have these conditions, so u is bounded with xu dash approaching 0, and we have this boundary condition at x equals L. So essentially these two represent our two boundary conditions. Then our solutions will just be this, where JV is the Bessel function, and our nu will just be whatever this was, and Kj will be our solutions to this problem. So suppose we just happen to get this question in the exam. We are asked to find the eigenfunctions of this equation. Well, we just compare it to what we have here. So nu squared equals 1, so nu equals to 1. And then our bounds are from 0 to 1, so here our L equals 1. And then if we compare this condition, so we have no problem here. We have u dash equals 0 at the boundary. So essentially that means C1 C1 equals 1 and C0 equals 0. Then we just copy the solution over. So the solution is so the eigenpairs are just these eigenpairs, and so our solution is just these eigenpairs where nu was 1, and kj is our solution to this equation, so, which is this, since C0 is 0 and C1 is 1. So moving on to the final topic, initial boundary value problems in 2 dimensions. In this topic, we get to partial differential equations, which can be quite tricky, but for the sake of this course, we use separation of variables, and this just breaks it into ordinary differential equations, which we solve using the methods taught in the other 4 topics. So to solve these problems, we assume that the solution is made up of univariate parts. So if we have a ux t, we assume this function can be split into 2 independent functions, with one function being of the first parameter and the second function being the function of the second parameter. And generally when we do this, we will get more than one solution, and so we have to use the Eigen Functions to create a general solution, and then we find the actual solution once we sub in the initial values. So here we have an example over here, and we're asked to use the separation of variables. So this operator is called the Laplacian. And what this does is just that differentiates first. I'll use this notation just to make it easier. So u is a function of x and t. Then we just take the second partial derivative of one of them plus the second partial derivative of the second xt of the second term, and adds them together. So this is the Laplacian, and we have that this is equal to 0. So if we apply separation of variables, we sub this in, then if we take the second partial derivative, that's just, so I'll just write this using xt just to make it writing easier. And this becomes x double dash t. Since it's a partial derivative and t is not a function of x, then we just differentiate x. And then similarly, this becomes xt double dash equals 0. And then we need to split this into 2 ordinary differential equations. So the process goes like this. So we divide both by x and t, and then we move 1 over to the other side. So we'll move t over, and we'll let this equal to some separation constant. And here I'll put in a minus because it makes things easier, but it's not necessary. If you don't, just make sure you're consistent throughout. So then now this becomes 2 equations which are connected through this separation constant. And this separation constant just makes writing things easier, right? So x double dash over x is no longer, we don't have to say that's equal to minus t double dash over t. We can just say that it's equal to minus lambda. So we move this over, we look at the x's. So move this over, this is x double dash equals minus lambda x, and then x double dash plus lambda x is equal to 0. And this is just a second order differential equation. And in fact, this is the Sternum equation that we looked at before. And we do the same for t. So we get minus t double dash equals minus lambda t. And then t, move the t over, t minus t double dash minus lambda t equals 0. And these are our 2 ODEs. So this is the general method for IVPs. So at least for 2221, generally your final exam will contain one long question involving one of these problems. But the process of doing them is usually always the same. So if you had practice with a few examples, then you should know what to do. But just as a reminder, the process is, first you apply separation of variables. So you sub in u equals xt, and then you split the partial differential equation into multiple ordinary differential equations, like I just did in the previous example. Right, we split this equation into two ordinary differential equations using this separation constant. And then we use the initial conditions, or the boundary condition and the boundary conditions, to solve the differential equations for x and t. And usually this separation constant still applies, so our solutions will be in terms of this lambda, although maybe not explicitly. So often we convert lambda into some n pi, for example. So we get solutions. We get a solution for x and a solution for t, and then we combine the two. And then we combine the two for a general solution. And they depend on the lambda. So I'll go for an example, which is the best way to get used to this. So here we have a problem, the heat equation. So this is our equation. This is, so x equals 0 and y x equals 1. This is our boundary condition, and then this is our initial condition, which is the boundary condition on t. So we apply separation of variables. So we let u equals to xt. Then we can rewrite this. So the partial with respect to t, that's xt dash equals x double dash t. And the boundaries are from 0 to 1, and t starts at 0. Here, so this means x of 0, t of t equals 0, and x of 1, t of t equals 0. Since we don't want a trivial solution, so this means either t equals 0 or x of 0 equals 0, but we don't want a trivial solution, so this means that x of 0 equals x of 1 equals 0. And then in the final case, this is our initial condition, so x of x, t of 0 will equal f of x. So these are our conditions, and this is our differential equation. So first we start with the differential equations. So we move the x is over, so x double dash equals t dash over t. Right, if we move the x and divide by x and t, then we say that's equal to some separation constant minus lambda. And here we'll start with x first, because we don't really have too much information on t. So we solve x first, since that we can do. So we move it over, x double dash plus lambda x equals 0. So as I did for the Stern-Lingual equation problem, the steps are the same. So there's three cases: lambda equals 0, and x equals ax plus b. But then if you remember our initial conditions, x of 0 equals 0, or equals x of 1. So this will be our trivial. This will be trivial. Once you sub in 0 and you sub in these boundary conditions, you will find that a and b are 0. This is the lambda of x. Secondly, if lambda is negative, so say minus k squared, which is negative, x equals to a e to the kx plus b e kx. Once again, this will be trivial. And when doing this problem, you probably know, if you've done it a few times, you can expect these two cases to be trivial. However, when doing this in an exam, you should still write it out, because it is part of the process. Because you need to show that you've checked these cases. You haven't just pretended that they don't exist. And then our final case is if lambda is positive. So then our solution becomes x equals a cos k pi, kx plus b sine kx. And using our solution from before, if we sub in our values, we'll find that a disappears, and our solutions will be in the form of b sine n pi x. And then, as a result, since lambda equals k squared, this equals to n pi squared. So this is our solution for x. And then now we need to solve for t. Right, so now we look at t and we move it over. So t double dash over t equals to minus lambda. So then t double dash, move the t over, then move it back. Get t double dash plus lambda t equals 0. And lambda equals n pi squared. Since this lambda has to be the same, we can just sub it in. So t double dash plus n pi squared t equals 0. And this is just a first order differential equation, so we can solve it right away. T equals to c e to the minus n pi squared t, where c is some constant. And now we solve both x and t. So now we just put them together. So since we don't have any initial conditions, we can't solve for c. So we just put the ux together, so the x and t together. So we combine the b. So notice that these depend on n. So we set this to be depend on n. So we combine them together. So we combine the constants b and c into some a, n, and this is the form where n equals 0. So n equals n. X equals sine n pi x, and then t equals to e minus n pi squared t. And then this is our solution for n. And then we what's the term? We superimpose. We add them together. So our solution, since these all solve the solution for this, once we rearrange them, we can all add them together since since if we add solutions of x, right, this will still equal 0, and similarly for t. So our solution, we just add them together. N equals 1 to infinity. We don't start n equals 0 since that case will equal 0, so we don't need that. N pi x e to the minus n pi squared t. And then now we have our initial condition. So we had one last condition which we haven't used, which is this one. So once we sub in u equals, so ux was 0 is equal to f of x. That was the final condition. So we sub in t equals 0. That means we have n equals 1 to infinity a n sine n pi x, and t equals 0, so e to the 0 is 1, so that's just 1. This is equal to fx. And we don't know what fx is, but we can, if we did, we can use fx to solve an. And the way we do this, since this is the odd part of the Fourier series, we can use that. So using the half-range expansion, so integral is from 0 to 1 since x is bounded between 0 and 1. And since the range is 1, then we have 2. So it'd be 2 over L, and L equals 1, so just 2, since we're just integrating half of the range. And then f of x sine n pi x dx. So then this is our solution essentially. So so u of x is equal to this where an is undetermined but equal to this. And sometimes if they do give an f, so if they give the form of the function fx, then you can solve this and you will have to. But regardless of what f is, the process up to this point is the same. And then once you get up to this point, you just integrate it. Integrate this depending on what f is. So for the last year's 2221 exam, f was a piecewise function, and essentially that just means you have to integrate this piecewise function times sine n pi x. Right, so that's the process of solving one of these partial differential equations. And it's a long process, but with a bit of practice, you can kind of do it without thinking. So you should probably just do it a few times, and then you should be good for the final exam, at least for this topic. If you get it in polar coordinates, so suppose we want to express our solution in terms of, we want to solve this differential equation using polar coordinates. So then, using the change of variables, our Laplacian becomes this. And then using separation of variables, since that's the only method we know, we let u equals to r of r and h of theta, since I'd rather not use capital theta, since it's more annoying to write. And then if you sub that in, so this is squared u equals 1 over r, partial with respect to r. So u with respect to r, that's just, if we drop the arguments, this is r dash h plus 1 over r squared, and then second derivative with respect to theta, so r h double dash. So the 1 over r using the product rule, so we have r dash h plus r capital R double dash h plus 1 over r squared rh double dash. So if you get a question that involves the Laplacian using polar coordinates, first we use this to transform our, so use separation of variables, and we plug it into this Laplacian, and we'll get this, which is rewritten here. So this was the Laplacian of u. And if we get this question, so we have three conditions. So firstly, u of 1 is so firstly we have a condition for r, so when r equals 1. And there's also another condition. So usually, since theta represents the angle, we want theta to be 2 pi periodic. So this is another condition that we add that isn't explicitly stated, but is one that is one that you can always add in and will be required. So I think I'll just skip through this, but basically you just once again use a separation constant to form you separate out two differential equations, and these are ordinary differential equations, so we can solve them normally. So this is a Cauchy-Euler form where we have this separation of constant lambda, which is undetermined, and this is the same differential equation we had before. So we solve h, and then we solve for r, and then we superimpose them. So we add them together. So this was r, and this was h, and for each k, so this is for each well, actually no, this is the generalized. Then we add them together, and then we use this condition to find the coordinates of AK. So we start at r equals 1, that's equal to f theta, and then we use that to find the coefficients. So this is a Fourier series, essentially, and we use it to find the coefficients. So from after that we have elliptic operators. So this is just another definition. So if we write our second order partial differential equation in this form, so this reflects all our second order partial differentials, either as a mixed partial or a second partial, and then we write this as the rest. And if we combine this into one matrix, then we say this elliptic if this matrix satisfies this property. And this is a bit of a random property, so but we have a theorem that can show whether an operator is elliptic or not. So if you get a question which asks to show that something is elliptic, you jump to this theorem, and what it's saying is that if we take the symmetric part of A, which is equal to A plus the transpose of A divided by 2, and we find the eigenvalues of this symmetric part, then these eigenvalues have to all be strictly bounded by a positive. So there needs to be a strictly positive lower bound within the feasible region. So note that just because they're positive, that's not sufficient. We need to strictly apply this definition. So we need to find a C which shows this. And this theorem is in if and only if, so it applies both ways. So if we can't show this, then we can say that, and we show that the C doesn't exist, then we can say that the operator is elliptic. And the point of elliptic operators is just that we can get a solution out of them. Although I don't think they get pretty complex, so I don't think you need to know anything more about them other than how to show an operator is elliptic. So I have this example. So we have an operator, and we're asked if this is elliptic within this region. So first you take the A. Remember, this operator has this minus in front. So our first entry would be this without the minus sign. So 2x plus 4, and then minus 3, minus 1 since the minus comes in, and then 2x plus 1 without the minus. And this is our A. And to see whether it's elliptic or not, we take the symmetric part. So take A plus AT over 2 equals that. And then we find the eigenvalues. So we do that by solving this, in case you forgot. So you find the L's that satisfy this. In our case, our eigenvalues would be 2x and 2x plus 5. However, within this region, so the region is 0, 1, even though both of them are strictly positive, we don't have a strictly positive lower bound. Because as x approaches 0, then 2x approaches 0, which means we can't find a strictly positive lower bound for these eigenvalues for all values of x. And as a result, this means that this operator is not elliptic. So yeah, as I said before, you just need to I don't think they'll ask too much about elliptics. At most, they'll just ask you to show to find whether an operator is elliptic or not. In which case, you just do what I just did. And finally, we have one. So I'll just go through one more example. Just so this is a problem involving an elliptic operator. However, it's nothing particularly new. It's really just another one of these equations. So, yes, thank you, Wendy. So, once again, we have this equation. We apply separation of variables. So now this is in terms of x and y. So u equals xy, and then this. So we translate this into our x and y. So x double dash y plus x y double dash plus lambda xy. Hopefully you don't get confused between my x's and lambdas. That's equal to 0. So then x, So we have x of x, y of 0 equals 0. So this is our boundary conditions for y. So y of 0 equals y of 1 equals 0. Now here we have our partial with respect to x. So x dash, and these are essentially boundary conditions for x, except here we're using the first derivative, but it's still a boundary condition. So x dash of 0 equals x dash of 1 equals 0, and that's our problem. So if we write this, x double dash divided by x plus y double dash divided by y plus lambda equals 0, then we get our two differential equations. So x double dash divided by x equals minus y double dash. So we move the y to one side. Here I'll just move it to the y, and then so you only have to deal with it once. And we'll let that equal to some separation constant. Since p is already used, we'll just use it. Since lambda is already used, we'll use a p instead. So once so you move the p over, you get x double dash plus p of x equals 0. Except here our initial conditions are slightly different. We have x dash of 0 and x dash of 1 equals 0. But apart from that, it's the same problem. So two of our solutions. So if p equals 0, this will lead to a trivial solution. If p is negative, this will lead to a trivial solution. And you can do it, and I think in an exam you probably should go through it. It's just because I've done it so many times. So our final case, p equals to k squared, we have x equals to a cosine kx plus b sine kx. And then we solve our initial equation. So first x dash equals minus ka sine kx plus kb cos kx, and we solve it in. So when we solve it in 0, the first term becomes 0, so we get kb of 1. So cos of 0 is 1, so kb equals 0, then b equals 0, so we know that. And then x dash of 1 shows 0 implies b equals 0. And then x dash of 1 is minus ka sine k is equal to 0. So for a non-trivial solution, we have k is equal to n pi once again. And then we solve for y. So for y we had minus y dash y minus lambda equals to minus p. Yep. So moving it over, get y double dash plus lambda minus p, I believe. Hold on, first. Lambda plus. hold on. Okay, I might have made a mistake in one of my solutions. But anyway, yep, so we get y double dash plus lambda minus p of y equals 0. I think I had lambda plus p. Oh, I think no, wait. Interesting, but anyway, what we do is we let mu equals this lambda minus p. And then basically we just get the same. So then we can just ignore this. So we just have the same problem, y0 plus y of 1 equals 0. And then if we go through the steps, since this is exactly what we had before, then y equals to a sine, I'm going to use m pi here, sorry, m pi of y, where mu equals to m pi squared. And then the question asks to find the eigenpairs. So these are just the solutions, so we combine it. So u equals to x, y, which is equal to, we ignore the constants at the front, so x was a cos kx, or a cos, so ignore the constants at the front. So the Eigen functions are cos n pi x, which is the x part, and then the yn part was here, so sine n pi of y. Yep. In our respective lambda, so since we let mu equals lambda minus p, then our lambda would equal to mu plus p, which is equal to, so mu was m pi squared plus p was n pi squared. And so these are our eigenfunctions, n. Okay, wait. So we have m and n here. We have lambda and n, and these would be our eigenvalues. And that's all we needed to do for this solution. So if we had an f to superimpose onto, then actually I wouldn't know how to do that. Oh wait. I guess you use some products to sums to convert this into a sum. But yeah, so essentially that's the end of this seminar. Yes. And also these slides will be available on the MathSoc website.